Forgot that little start recording button. There we are. Good morning, good afternoon, good evening to people around the world. This is Martin Hubel, your host of the DB2Night Show, and I've got a very special guest with me today, Dan Luksetich. Hey, Dan. How's it going?
Hello. It's going okay.
Good. We have that big, wet, fluffy snow coming down today that if you go out and stand in it, you get them all over your head, and all of a sudden you feel wet. It's really cool. It'd be really cool if it was a weekend where people didn't really have to drive in it. Of course, most of us are working from home these days, so frankly, it's the old saying goes, I could get out my trombone and play Let It Snow for you, because I'm at a point where I care less about how the weather is outside, even if it is frightful and all that other stuff.
I remember a job I had once in Toronto, and I actually got snowed in.
Yeah.
So what was to be a 4-day job in Toronto ended up being a 6-day job because I couldn't get out of town for 2 days when the snow shut everything down.
Yikes! I was late getting into Bergen, Norway once because I went through Frankfurt and they had a half a centimeter of snow, and that was because people wanted to be de-iced. They didn't have the equipment to de-ice all the planes, so I literally showed up at 2 o'clock on the first day of my assignment. So snow days and travel. I really don't miss them during COVID here. Okay, let me get this housekeeping out of the way so we can get on to your great presentation. This is our social media. The main thing to note here is our hashtag on Twitter, DB2Night, and that replays are available on YouTube. And that seems to be fairly popular, so that's a good thing we're able to do that now. And you'll be able to get to that link through the replay blog, as well as downloading the WMV and MP4 replays as well. Here's our famous disclaimer. Basically, we're recording the show. We respect any trademarks of the various organizations of who they are, and we'll be putting things up as a replay later on. So there you go. And our quick announcements, which is basically about our next shows coming up. We'll do some studio audience polls. I don't know why that says all about iDoug. I must have grabbed this from somewhere, but it's actually Dan there. Golly. It's amazing how many typos I can put into a presentation or not take out. Our upcoming shows for January and February, we do have our LUW shows booked. We have Kerry Romanoff speaking on DB2 1155. I think these people have, what do they call it? Dodecaphobia, which is fear of the number 12. I don't know why they just don't come up with DB2 12. Apparently dodecaphobia is a known thing, similar to triskaidekaphobia, which is the fear of number 13. And then we have Michael Tiefenbacher talking about recursion. I've seen this presentation, and it's fabulous. When he offered and make this available, this is one that it's a must-see presentation. I
agree.
I believe that would also be appropriate for the people on ZOS as well. As for the Z shows, I've got a number of requests out to various speakers in both the IBM lab and other places in IBM and other consultants. So watch the space. January 29th is the first show on that side. And as always, we have the DBi Performance Webinar available for DB2LUW. And there's a link off the DBi software page. And if you watch the demo, you get to, they'll send you a gift card, I believe. And our winner from our last show, our lucky drawing, is Wanda Yang of RBC. And actually, this is the first because it's our first Canadian winner of the DB2Night Show Weekly Award. So that's fantastic. And we actually sent her a gift card for Amazon Canada. And our sponsors are DBi Software and yours truly, Martin Hubel Consulting, Inc. And here's our bit of humor, just as a public service reminder. As days get colder, animals are attracted to the warmth of car engines. So make sure that, if you live in colder climates, to check your wheel wells and other hiding places, because you never know what's going to show up. I'm guessing this was photoshopped. But there's a hashtag up here, meanwhile in Canada, and there you go. And all right, let's get on and do our polls. We have our standard first question that we're going to ask, which is, what's the newest version of DB2 on Z that you're running? And you click in there. We give you about 30 seconds to vote. Normally is enough to get people going on that. And we're getting up to that number. Well, a lot of people have voted, so let's just close that off and share the results. And we're getting an awful lot of people on 503 and higher, which is fantastic news. That's great. And fewer and fewer people, as it turns out, are on DB211, which is even better news from an IBM point of view, because they love to have their customers run the latest stuff. Now, this is an interesting one. What's the modern language of choice for your DB2 applications? We've got 3 listed there, but if there's one you use that we forgot to put down, I'd be quite happy to have you write that into us. It's always fun to see what people are doing. We've got COBOL, Java are big. This is an interesting question for me, Dan, because I was teaching at a community college, and they asked us when we were doing curriculum planning about 3 years ago, and the response was interesting. They came back and said Java was a legacy language in their minds. I thought that the only thing they were really interested in was Python. And,
yeah, I was on the EMEA application developer panel, and I think Python was mentioned almost as often as DB2 was mentioned.
Yes, yes. Interesting. We've got SQLPL as mentioned as well, and there's our good friend Locke. Locke Lyon is still out there working away. That's great to see Locke. Locke and I used to work together 30 years ago. So it's always fun to see good friends. And our next question is, are you using temporal tables? And this is there was an awful lot of hoopla about this when it came out 10 years ago. And of course, there's some things that when they first come out, everybody says they're going to look into it and do it. And then when you look back at it sometime later, it's interesting to see what's going on. And as I look at the question today, this is pretty much what I'm expecting to see. But I'll give it a few. We've got 70% of the audience. We'll give that a little more. We've got a nice, good-looking audience today. And let me close that off and share that result with the audience. So we see that 41% of the people are using system period. Some people are using application period. That's great to see. And 9% are bitemporal. And 14% are planning for the future. And 23% are no. Interesting. Why we love these surveys. They should tell us a lot about our community. And the next one is, are you using the DB2 for ZOS developers extension for VS Code? And so it would be interesting to see here. Knowing how votes go, it was 100% of our audience for the very first vote, and then some of the no's caught up. How does that work? And we've got a few more people coming. The votes are still coming in. We're going to count all the votes, because I don't know how not to count some votes. And so we'll close that off now. And you see 70%, 77% no. We have 9% yes, and the other 14% are planning. So that's another interesting thing to note. And what we'll do now is close that off, and I should be going back to seeing my screen. And now, oh, there's another quick commercial for DBi software. This is just their main panel showing you what's happening in the DB2 LUW system with system overview in terms of good performing, bad performing, etc. It's useful information to get you to go to the right place to fix problems, and also to see what your service levels are like. And with that, Dan, I'm going to turn control over to you. I'll be making you the presenter. You should have a thing to click on your screen.
Yep.
And I see your screen, so we're ready to go.
Okay.
I'm going to be watching the. Got some other people. Sorry, I was just looking at the question queue to see if there's something that worth saying before going, but it's mainly just friendly comments from good friends. So I'm going to mute myself, but I'll be watching the question queue, and as needed, I'll break in and.
Okay. Yeah, I do not see the question queue, so.
Yeah, that's because I'm an organizer, and you're just a very nice presenter.
Okay.
But I'll be here watching it for you.
Okay. All right. So just a little bit about myself. I've been working with DB2 since 1990, and a DB2 consultant since 1995. I've had lots of different jobs. I've worked on DB2 on iSeries, Linux, AIX, Windows, and ZOS. Does this mean that I'm an expert in the field? Even though my website is db2expert.com, the fact is that I don't think there are any experts, because the breadth of features, the hardware, the software, it's always changing, and you can never be, you might be an expert in one facet of DB2, but not everything. So there are some things that I'm good at and some things that I'm terrible at. The bottom line is that the information I'm going to give you in this presentation is information based upon my experience, which might be valid for my experience, but might not necessarily be for yours. So the bottom line is to question everything I present and test it. And I'll talk a little bit about ways you can do that at the end of the presentation. Also, we've made the notes pages available for download. And there are lots of things in the notes pages that I'll probably skip over during this presentation. So please download that and read the notes. So as an overall performance overview, we're looking at, if you're wishing for high performance and low cost, it has to be part of the design. So a lot of times we're deploying generic database designs in support of an application, and not much development time has been spent into designing the database with performance in mind. If that's your situation, then you're going to be doing a lot of firefighting, et cetera. And there are certain things that you can do to make things better. But if you're really looking at an application process that is going to be a high performance process, or high volume process, that you really need to make performance part of the design choices. And there are certain things that you can make as far as the physical design of the tables and indexes, as well as application design with consideration of the physical objects in mind. This presents a specific challenge for us database people, in that we have to establish a relationship with the application developers that is mindful of the performance considerations for the database that we're deploying on. and that could be a significant challenge. So it's something to convey to management and see if you can get them on board to at least have some semblance of design considerations for performance. So sorry, I'm trying to get this go to meeting stuff out of the way. Okay, so just an overview about index choices that we have before I get into particular performance issues. So there are multiple basic design choices for your indexes and for your tables. You can have partitioned indexes, which include a partitioning index, which has been deprecated, and non-partitioning indexes, those being the data partition secondary index and non-partition secondary index. And we'll get into details on what those are in the next few slides. There are other index choices, including index on expression, which includes JSON indexes and XML index as well. So these index choices need to be explored in detail when making design decisions. This presentation is only going to sort of gloss over the different types of indexes. So you do need to have an understanding of what these are and the differences between them to fully understand what's going on with the indexes. Oops, now. Okay, so DB2 indexes use an optimized Btree implementation. So Btree stands for balanced tree, and it's a common index design across lots of relational databases. The index could be between 1 and any number of levels, depending upon the number of index entries and the page size that you're going to be using for the physical deployment of the index. So these multiple levels mean that you can have a root page, right? All this stuff is based upon the index key columns that you're specifying for the index, and so what you have at the top of this Btree is what's called a root page, and the root page may or may not point to leaf pages, or could possibly point to non-leaf pages. And what a non-leaf page is another level in the index which points down further to other non-leaf pages or leaf pages. And finally, the leaf pages contain key values and associated RIDs or row identifiers that actually point to the data in the corresponding table that the index has been associated with. And I want to talk about partitioning for a moment here. All modern tables in DB2 for ZOS are partition tables. They're either partitioned by range, which means that the data is physically split by designated column values in the table. Those partitioned by range tables can have index that can be partitioned, or they can have non-partitioned secondary indexes or data partitioned secondary indexes. And then we have partition by growth tables, where the data is physically split by a designated data size. Column values play no role in splitting the data up, and every index created is a non-partitioned secondary index. So the biggest difference between a partitioned index and a non-partitioned secondary index is that for all of your table space partitions, and in this particular example, I have a partition by growth table spaces in n parts. A non-partitioned index is going to point to data across all of those partitions. So that's the big difference between a partitioned index and a non-partitioned index. Now, there's also the data partition secondary index, and in that, like a partitioned index, we'll have one physical index partition per table space partition, but that is still split up by the partitioning column values. But the key in the data partition secondary index is it does not match the partitioning key, whereas a partitioned index, the beginning values of the key match the beginning column values for individual partitions. So what are the advantages and disadvantages of these types of indexes? Well, if you have a partitioned index, you're going to have multiple smaller index parts depending upon your partitioning scheme for your underlying table and table space. What this typically means for large tables is that you could potentially have fewer index levels. Now, these pages within an index represent potential physical IOs to the underlying data set that the index is being stored in. So if you have an index, say, in 5 levels, you could theoretically incur 5 separate IOs in order to eventually traverse the index Btree and go to the data row. Whereas now, if you have a partitioned index, you're going to be dividing your amount of data that you're indexing into smaller chunks, smaller physical chunks, which might reduce the number of index levels that you have to traverse to get to the data. So that is one advantage of creating partitioned indexes. I like to have this philosophy in that, do I want to manage one great big giant thing or lots of small things? And typically I found it easier to manage lots of small things in my database as opposed to larger objects. So when you partition an index, you're going to be busting that up into physically smaller pieces. And that could be possibly easier to manage depending upon whether you want to manage lots of small things or one large thing. But I found it typically that managing lots of smaller objects is a bit easier than several large objects. Also now with partitioned indexes, you have the potential for utility, SQL, and application parallelism. So this means that you can take advantage of DB2's built-in parallelism, which I've used quite extensively with absolutely fabulous results against very, very large tables. And utilities as well can take advantage of parallelism on partitioned objects. Also, for some of my very highest volume applications, I've employed what's called application parallelism to actually split up work on behalf of the application into multiple pieces, run those pieces corresponding to particular partitions for really high performance. And with partitioned indexes, you have a potential for higher availability. You can take down one part while leaving other parts available. So as far as non-partitioning indexes goes, you have your data partition secondary index. And this also means you might have smaller index Btrees and potentially fewer index levels then. So potentially fewer IOs for a particular request. Again, you're dealing with smaller physical objects, so they could be possibly easier to manage. And you also have potential for utility SQL and application parallelism. Now, the SQL parallelism depends upon partitioning columns in the predicate. There's an optimizer method called partition elimination, where the DB2 optimizer is able to eliminate partitions from your query's physical access depending upon partitioning columns. Now, these columns have to be present in the predicates of your SQL statement in order for this partition elimination to occur. If not, data partition secondary indexes could potentially be a performance hindrance in that any SQL queries might have to probe every single one of the index parts in order to satisfy a query. So that's something to be aware of when you're considering these types of indexes. A non-partition secondary index is one potentially very large index, and therefore you have one Btree to traverse for queries. This could potentially mean more IOs and slower response in that regard, but you have potentially improved access, especially over a data partition secondary index, in that you're only traversing a single object, and that could be depending upon the columns in the predicates in your query, it could be a performance advantage. And then you have availability and performance implications for utilities because you're dealing with one very large object as opposed to lots of smaller objects. So I'm going to go into some basic design concepts before diving into indexes. And when I'm working on a new application or a new database, one thing I most certainly initially consider is this going to be a high read versus a high insert or update application? And the standard rule in the past used to be 80-20. Well, we're 80% reads and 20% insert update. That's not necessarily true anymore because with the advent of faster machines, faster DASD devices, and needs such as auditing, history requirements, governance, and things like that, we now have these applications with just ultra high ingest rates. And we now have to be more serious about these considerations. Well, how often are we going to be reading versus changing the database? And if your application is truly a high read application, 80-20, then you could make more indexes on tables. Clustering can be an important issue as well, and we'll talk about that a bit more in upcoming slides. If you got a high rate of inserts, you might want to think about fewer indexes on your database, and of course clustering is less important because if you're a high rate of inserts, you're looking at making those inserts as fast as possible. And if you think about it, clustering, which I'm sure everyone knows what clustering is, but I'll explain it anyway. Clustering is DB2's attempt to keep data in the table in the same order as it is in a particular index. Well, that's going to take resources to find that spot that's available in a table. And if you're a high rate of inserts, that could be very expensive for your operation. What about high updates? You have possible free space considerations that you have to make for your tables and your indexes. And none of this matters at all unless you know what your service level agreement is with developers and with management. One of the things I hate the most about going in and meeting with management and saying, well, how fast do you want this application perform. And typically, unfortunately, typically the answer is, well, I want it to run as fast as possible. And my answer to that is, well, that's great. Buy an infinite number of machines. And when they object to my response, I said, well, okay, now seriously, we need a number. We need a performance expectation if we're going to build an application that can satisfy it. As fast as possible means that, you know, it's unobtainable. So you need to know what is expected before you're going into these designs. Okay, so let's talk a little bit about clustering. Clustering is DB2 attempting to keep table rows in order of the clustering index. On DB2 for ZOS, a clustering index is either specified as the clustering index when you create the index, or it's by default, meaning the first index that was created against the table is designated as the clustering index. The actual index keys are always kept in order in the index. DB2 attempts to keep the data in a table in that same order of the clustering index. So this is an important thing to know for your applications that are accessing tables, especially for your given transactions or your processes that are the most frequently executed. And you know, you all know what those processes are, right? There's you know, in every application design, there's a handful of transactions that are sort of the core piece of the application that are accessing the same tables all the time. And when this happens, DB2 can take advantage of certain performance enhancers. In particular, I'm talking about dynamic prefetch and index look-aside. And these are features that were built to handle these repetitive accesses into these objects. And this all depends upon clustering on the data side. You can really take advantage of these performance enhancers if you're clustering on frequently accessed values. So this is a good thing to, you know, consider when you're building your application. You're taking a look at the most frequently accessed tables and what indexes are going to be used in the access path, and perhaps consider clustering on those particular values and across for common tables as well. So common cluster across multiple tables is really good for joins and for random readers in general. You know, again, going back to your most common transactions and processes, if you have you know, a transaction hitting the same tables at the same time, or you're coding a join between these two tables, then you're probably going to want those tables in a common clustering sequence. Especially true for, you know, parent tables and child tables, where the child is inheriting a key from the parent. And we'll talk about more about that in upcoming slides. But this common cluster is important for frequently accessed tables. Within a table, how can you maintain clustering? Remember, the indexes are kept in key sequence, so we don't necessarily have to think too much about that for indexes. But how do we maintain cluster within a table so that the index access for this frequent access path is matching the table data? And the key is free space. So if you have a table that has high volume of inserts, you could require a certain amount of free space. And that has traditionally been the PCT free setting at the table space or partition level. We also have free page at the table space or partition level. That should primarily be ignored, except for tables that have an extremely large row length, in that you can't get more than 1 row per page. So percent free, typically I set percent free based upon the insert rate prediction for uniform distribution. You know, that's typically not the case, but it's the best you could do because percent free is being set at a table space or partition level. I usually typically use the sys table space stats catalog table to predict what I should set percent free to. And that is the desired number of days between successive reorgs of the table space. Now, recently new, I think it was introduced in DB2 for ZOS, if I'm not mistaken, is the percent free for update setting, which I've recently been using on my tables quite a bit to solve a number of problems when we have rows being updated in a table and the row length changes. One thing to keep in mind is percent free and percent free for update equals the total free space you're going to specify for a table. Okay, now back to partitioning. When am I going to choose partition by growth versus partition by range? And basically, I'm going to do partition by growth unless there's something special about the table. And either that's going to be the table is going to be very, very large, or I have some other thing. I want to improve availability, have a meaningful separation of parts based upon some philosophy, you know, geography, date, something along those lines, or just random distribution of parts. This way, it might be a higher potential for availability in that I can take a particular partition offline while other partitions, you know, remain available. Theoretically, you know, I could have one partition per country that I serve. Okay, and we're going to take country A is going to be offline for maintenance, and while other countries still have access. Range partitioning also allows us to perform utility operations on a subset of partitions. I believe you can do this to some extent with partition by growth, but primarily I do it with partition by range table spaces. Improve manageability. I can, you know, I'm taking a very large table and splitting it into smaller parts. I consider the smaller things easier to manage than the bigger things. And improve performance. So when it comes to parallelism, both application inspired or database controlled, you have more flexibility with range partition table spaces than you do with partition by growth table spaces. So this is an example of what I do when I'm splitting up a table. Let's say it's a very large table and I'm splitting it up based upon range partitioning. So instead of having one giant table and one or more giant indexes, I have several smaller table partitions and a corresponding index partition. In this example, I have a system generated key, a UUID that goes through an interpretation, and it generates a partitioning value, and that allows the data to be split somewhat randomly across multiple partitions. In this case, the primary axis is going to be via the partitioned index, and that is also the clustering index. In this particular case, I've got high volume ingest application doing hundreds of millions of inserts. I can split that process by my part values into multiple individual processes, run them in parallel against the individual parts for a faster overall smaller runtime. And this alleviates a lot of different problems in that not only are you running in parallel, but also each individual application process is acting against an individual partition of a given table or tables, which also could be distributed in a data sharing group across multiple members, and avoiding any overhead associated with global contention. So in being able to do this, in my experience, we have achieved ingest rates of around 80,000 rows per second. So getting back to index design and performance considerations for indexes, the first rule is to build only the indexes are needed. If in this case we're talking about processes that are modifying data, then yes, you want to build only the indexes you need. If you have a truly read-only database, then you can create as many indexes as you'd like. Start with one index, and here's the challenge. This index has to serve multiple purposes: primary key, clustering, range partitioning, foreign key support. If you look at the right side of the slide, I've got a parent table and a child table. The parent table has a key. Primary key of CK1 is the column name. The child table inherits the primary key of the parent table as the first column of the primary key of its table. That's called an identifying relationship. That's really important for maintaining this common cluster across multiple tables. And also, it helps eliminate the number of indexes on child tables. If your child table does not have an identifying relationship with the parent table, that means you're going to have at least 2 indexes on the child table, one to support the primary key and one to support the foreign key. You want to try to reduce that whenever possible for tables that are high volume. So what does this mean? Well, you have to use natural primary keys. You know, if you have a customer identifier, you don't want to build a table that has a primary key of a UUID and a secondary index of customer ID. You've already sort of incurred more overhead by introducing this UUID, system generated key. And you know, that's the great challenge in modern application development, because a lot of deployments you're going to see are based upon object technology and object relational mapping. Everything gets a UUID, and we'll talk about more about that in upcoming slides. So you want to lean towards natural keys, but if you can't, you at least want to make sure that you have some identifying relationship. And I'm not telling you to go out and fight your application developers over whether or not they're going to use system generated or natural keys in their tables, but you basically want to pick and choose where it's important and where it's not important. Not as an overall philosophy, but you're just targeting the tables and indexes that are going to be your high volume objects. And the principle behind this philosophy is that every additional index introduces a random reader for inserts, for deletes, for updates that change the value of an indexed column. So you want to make sure that initially you're keeping the number of indexes to a minimum. This system generated keys, like I mentioned, do contribute to index proliferation. Identifying relationships are going to help even for system generated keys. So you can say, well, yes, we understand the philosophy of system generated keys, but for these particular tables, at least we set them up with identifying relationships. In other words, for a child table, instead of having a particular UUID as its primary key would be the inherited UUID from the parent table concatenated with the UID of its table. And perhaps that's more accommodating to the application developers than natural keys. Okay. Within the index, we can specify free space in the form of %free and free page. And remember, indexes are always kept in sequence. However, they could become disorganized if, like the index example you see here in this picture is pretty much, perfectly organized. But pages can get out of alignment physically within the index data set, which could lead to pages that should be pointing to other pages that are relatively close in the index structure, ultimately being far away in the index structure because the index has become disorganized based upon the frequency of inserts and perhaps updates as well. So even though the index keys are kept in sequence within the index, the actual physical organization of the index is subject to becoming disorganized at times. So the way you can alleviate some of these issues is to allocate free space. And we could do that via %free and free page. %free should be utilized to avoid index splits between reorgs. So if an index page fills with information and DB2 has to insert another entry into that page, it's going to have to split the page. And splitting an index page can be very expensive, especially in a data sharing environment. When an index page has to be split, a latch is actually taken on the root page of the index. What this means is that if you have multiple processes inserting entries into an index, and one of them has to split a page, that means if any of the others have to split a page, they have to wait for the process that's splitting the page first to complete its page split before any other process can do it. So splitting pages is a serial process. So the goal of setting %free would be to anticipate the number of new entries that you are going to place in an index in the time between index reorgs. The goal is to encourage no index page splits between index reorgs. So again, I'm relying on catalog tables to tell me this information. In particular, sysibm.sys index space stats will tell us, will give us an idea of the number of pages that have been split since the last reorg. Now, because setting %free assumes a uniform distribution across the entire index, that isn't necessarily realistic. So you might have areas where hotspots within the index where you're incurring more inserted entries, and you can avoid splits between reorgs. This is where free page comes in with your index. You want to allocate free pages if you can't avoid splits between your reorgs, such that when DB2 splits a page, remember when it's splitting a page in the index, it has to find a full page to put half of those index entries. If it can't find it within, it'll do a search algorithm looking for a nearby completely free page. If it can't find that, then it's going to have to tack that new page onto the end of the index. And that could lead to some serious disorganization. So you're going to want to specify free page when you can't avoid splits, and do so in a way that DB2 can efficiently find a free page when splitting.
Dan, I've got a question in here from a little while ago, but it applies to %free and free page. Is %free for update applied at reorg time or insert time?
%free for update is implemented at when you specify it.
Right.
So
I guess
if you have free space available on a given page in a table space,
sure,
and you specify a value for %free for update, it's going to reserve that whatever space that is up to the %free for update that you designated.
Right.
So it's immediate.
And that would then be, if I reorged, I'd be restoring that space at that time?
That's right. If you reorg, you're going to allocate all free space, which is %free plus %free for update. And that %free for update is going to be reserved specifically for relocating updated rows. This setting has been a tremendous performance advantage for applications that I've been working with, in that it has virtually eliminated the need for reorgs on some tables. Also, it has greatly reduced the amount of synchronous write IOs and synchronous log IOs in a data sharing environment when we've had significant global contention across partitions. Group buffer pool dependency can lead to tremendous synchronous IOs for these row relocations. And if you can avoid that for %free for update, you're going to save a lot of time. And we're talking hours versus minutes.
Perfect. Thanks. And I would also just like to point out to folks, Dan was very kind and gave me his PDF ahead of time. So as a studio audience attendee, you can download the PDF anytime you want during the presentation. It'll also be on the replay blog later. Thanks.
Okay, so even when partitioning, you could have very, very large indexes. And I've always taken a standard approach of allocating table spaces and indexes using 4K page size. That's sort of been my generic approach since day one. I've only done larger page sizes when absolutely necessary. And the funny thing is like for you know, I have pretty good relationship with IBM's DB2 development staff, and occasionally they would bring up something like, you know, Dan, why aren't you using larger index page sizes? You know, I'm like, well, I don't know. It never really occurred to me. And as I started dealing with larger and larger objects, I noticed that even with these modern DASD subsystems, and a lot of them are SSD now, we still get significant I/O times for these large 4K page indexes that have random access. And this is because the leaf pages are very distant from each other in these big indexes. And there's a small subset of pages that are cached in the buffers because of the index size. Index look-aside is rendered irrelevant because the data is randomly accessed, and you know the leaf pages are very far away from each other. And so it's a big challenge now. So one solution might be to employ a larger index page size. So if you have a larger index page size, you're going to have certain better efficiencies. Also, you might want to investigate having a larger page size in combination with index compression. So one example is I've got a very, very large random index for a system period temporal history table that consumes 12% of the I/O and 9% of the response time within an application. And these are just for the inserts, for the system period temporal history inserts. And that was quite shocking to see that. So I explored making the 4K pages 8K pages, and there's a really big advantage to increasing the page size for your indexes. For one thing, there's fewer pages, and my argument against in the past used to be, well, I have one 4K page, or I'm sorry, two 4K pages versus one 8K page. Well, if I'm going to do a physical I/O, in the first instance, I'm going to be doing two I/Os to get two 4K pages. In the second instance, second one, I'm going to be doing one I/O, but I'm going to be reading 8K. So I'm going to be reading twice the data. Isn't that sort of the same thing? And the answer is, well, yes and no. But the real advantage is something called improved index fan out. And what index fan out is, it's the number of children in a node of in a Btree that could be pointed to. So in other words, if you have a non-leaf page and it's pointing to n number of leaf pages, that basically represents the index fan out. So when you increase the size of a page, you improve the index fan out. A non-leaf page is going to point to more leaf pages. So I've got a simple example here. Let's assume index 1 has 137,160 active pages. 136,120 of them are leaf pages. That's 1,040 non-leaf pages and a fan out of 131. If I increase the page size to 8K, that cuts the number of leaf pages in half. But fan out is increased by a factor of 4. That number might be that might be 2. That might be that might be an error in my presentation. But yeah, it is. It's a factor of 2. But now we have 68,010 leaf pages and a fan out of 261. So we've doubled the number of leaf pages that can be pointed to by a non-leaf page, which means that we've reduced the number of non-leaf pages at a ratio of 2 for 1 compared to the reduction in leaf pages. What this means is that you have the potential to retain more non-leaf entries in the buffers. In this case, approximately 2 times the non-leaf entries within the buffers. This means that your buffer utilization will increase, and perhaps you'll reduce the number of IOs that that are being requested in support of non-leaf pages and traversing the index. We also have the opportunity for index compression. So index compression will reduce the number of leaf pages, but not necessarily for the non-leaf pages. It does not save space in the buffers because indexes are only compressed on DASD. So when they're read in, they're expanded within a buffer pool. But you do get the improved fan out, which goes with increasing the page size. And that for index compression, you're going to be using a larger index page size anyway. Be careful when employing index compression, because you could be saving space or you could be wasting space. So definitely you want to use the DSN1 comp standalone utility to predict the amount of savings you'll get from compression and the various page size choices that you could make. Now, Brian Laub of the IDUG Content Committee wrote an excellent blog article on compression, which goes into some significant detail and is worthy of a read in regards to index compression. I've got a link to that at the end of this presentation. Let's do another comparison of this change in index page size and the resulting improvement in fan out. So a high fan out makes the tree bushy and thus more efficient. Previously, we're using a 4K page. It's in 5 levels, and we've got a fan out of 131. If we go to an 8K page, we could potentially reduce the number of levels in the index because you've got fewer pages, and you have this improved fan out. Your buffer savings for non-leaf pages is improved by double, actually, because more non-leaf data could possibly be held in memory. So that's important especially for these really big indexes. Okay, let's talk a bit about modern application development. So we've got this service-oriented programming, agile development. One of the things I noticed that I wanted to mention is that one thing I'm seeing is that services, especially microservices, are being called way more often than they should be. So that's one thing to be aware of, and hopefully you've got monitors that can track this sort of thing. This has been one of the bigger challenges. Now these applications are using system-generated identifiers as primary keys for their database objects. So they could be random bit strings, random or incremental sequences. Typically, these are universal IDs or GUIDs, which are a 16-byte random bit string. UIDs, which could be a variety of numeric or random bit strings of varying data type and length. They might be sequential, they might be random, I don't know. It's sort of the Wild West out there. DB2 can provide UID and UUID values via the generate unique and generate unique binary functions. So they can provide equivalent ID styles of UID and UUID. However, they're based upon the internal clock. So they are sequential in nature when assigning new IDs. You also have DB2 sequences, which can provide unique identifiers, which typically DB2 sequences are assigned sequentially. So you want to be careful when you're using these identifiers and be mindful of their impact on your tables and indexes. So GUIDs are truly random. So you might want to employ a random reader design. That's the situation where you might want to use identifying relationships. You might want to make sure you've got your clustering right. Shoot for a common cluster. You're going to want free space in your tables and your indexes. DB2 generate unique and generate unique binary. They're sequential because they're based upon clock. So you might want to do then a high insert design, because if these are the primary keys, new information is going to be going into the end of your object, your tables or your indexes. So free space might be irrelevant in this situation. DB2 sequences may be again kind of the same thing, where you're all the new data that you're adding to a table is going to be tacked on at the end. So free space might be irrelevant. It was a kind of funny thing because occasionally when I'm working for a particular customer, it may be a slow time. So there's not a lot of demand for my work and stuff. And so I just go and look around. And I was at one of my customer sites, probably middle of last year, where it was kind of a quiet time. And I decided to do a review of all the production objects and free space. And it was really interesting because I found quite a number of objects that had sequential identifiers as primary keys and significant free space in the indexes. And I went in and redefined, I redefined the indexes as I altered them %free 0, free page 0, and reorged them. And we saved a lot of DASD because as a situation in many places, we're outsourced and we pay for how much DASD we use. So we initially saw a significant reduction in our DASD costs, but also we got a potential performance improvement because now our indexes are smaller. And perhaps we reduced levels on some of them because all this free space that was never going to be used. So that's an important thing to keep in mind. The same thing is true for DB2 sequences. So GUID's random. You want appropriate free space in your indexes. For the other values, maybe you don't want the free space because you're not going to use it. And just, you know, this is my recommendation. Obviously, with proper understanding of the applications that are adding data to the tables, and proper monitoring will really tell you what the story is in your environment. And that gets us to testing. Now, I'm only going to touch on testing here. I'm hoping to put out a new blog article later this month where I'm going to go into details about testing. I'm a consultant. I work on databases. I'm not normally, I don't have access to all the cool performance testing features that are available to application developers. However, whenever I'm making a decision about a change to an object or a new object, I'm performing tests against it. So it's not enough for me to read up on it, to look at all the recommendations coming from various consultants or IBM or whatever. I'm gonna test my design choices. And it's not at all difficult to build and test a database design. You can use SQL to generate data. You can use SQL to generate test scripts. There are several tools that can make this totally easier and possible. And I promote the use of DB2 accounting traces and reports if you have access to those. Hopefully you have access to some sort of monitoring tool. Otherwise, you're going to be, you know, looking at your watch during the test, and that's not always the completely accurate way to monitor. Here's some of the tools that I use depending upon the situation. Spoofy, Rex, PL/SQL stored procedures to test local access. Yes, if I'm going to test a particular index or table design, I could write a PL/SQL DB2 native stored procedure and put a loop inside the stored procedure to test various things across multiple iterations. For big queries, sometimes I'll use Spoofy or DSN-TEP2. I've got Rex programs to test invoking stored procedures or running queries to test I/O or CPU consumption of SQL statements. If I have a requirement to test performance over a network, I'll use such tools as DB2 Batch. Lately, I've been using PowerShell quite a bit. There's a lot of support out there for PowerShell, and getting PowerShell working with DB2 is super simple, and you know, just easy to do. I've also, in the same light, used Linux and Unix shell scripts. I've written small Java programs to test remote testing. I recently set up a test for the setting client user ID from a Java program, and I was able to do that on my workstation in just a few hours. Using IBM Studio and using the VS Code DB2 developer extension is another way to do some testing. And like I said, I'm going to be coming out with a blog article later this month that's going to go into detail about how you go about setting up some of these tests. As far as monitoring, DB2 traces and reports are the key. You've got statistic traces and accounting traces. Hopefully you have some way to get those reports. I perform regular monitoring using accounting and statistics reports because I want to look for trends. If you don't necessarily know something is wrong unless you know how an application process normally behaves. So hopefully you have some tools available and you can accumulate information over time to know about how your applications respond. So you can do things like, oh, well, I'm looking at an accounting report for an application that suddenly is behaving differently. Response times are elongated. What's the problem? And this is an example from one of my customers where it's pretty obvious what went wrong. We've got some sort of locking and global contention issue. And that'll say, well, this application was normally not experience these sort of things, and all of a sudden on this particular day, something went wrong. And you can go from there and start digging in deeper. I also do this. I take accounting information for a given application and bring it into Excel and report on it using graphs. That makes things like this example quite obvious. Oh my gosh, in September of 2017, something significant happened, and we got to look into it. Now, in regards to monitoring indexes, I monitor using the real-time statistics catalog, sysibm.sys index space stats. And I've got a really nice query that I wrote, and it's out on my website for you to be able to cut and paste it. And I basically use it to tell me when indexes need to be reorged. But also it's important to monitor those stats between reorgs to see how well your free space implementation is doing. And key stats within sysindex space stats would be reorg leaf far, and there's a reorg leaf near as well, the number of extents, number of mass deletes, the number of levels. Another thing that I think is important is that you separate indexes into their own buffer pool. Table data and index data are going to have different access patterns, and it's nice to keep them separated so that the behavior is consistent within buffer pools. Also, separating the index into their own buffer pools gives you additional information for the indexes. So if you're looking at your accounting report and suddenly you have a change in the behavior of an application where suddenly there's a whole bunch of additional I/O, you could look at the buffer pool section of the report and quickly identify whether your I/O problem is index related or table related. So it gives you further insight into that thing. And then obviously, if you have a high volume index or a particular index that's of interest, you might want to separate it into its own buffer pool. Here are multiple references to additional information on this. There was a question earlier about percent free for update. If you go to my website, db2expert.com, I also have a blog article on that particular feature that goes into great detail about it. I mentioned Brian Laub's index compression article. You do have to log into the IBM's website. A membership is free, and once you're logged in, you'll have access to that article. And that is it for this presentation. I hope you enjoyed it, and hopefully you've learned something.
All right, great job, Dan. I've got a couple of questions, believe it or not, from a guy named Brian Laub.
Hey, hi, Brian.
And the questions are, the acronym RID causes confusion. I believe the long-term form is record ID. Sometimes people use row ID. Do you differentiate?
Yeah. It is a bit confusing. I use record identifier, I believe is the proper terminology, but if you use the RID function, that delivers something called a row ID, but they're one and the same.
Right. Yeah, I kind of hear them being used interchangeably myself through the years. And another question, you mentioned recommended accounting trace classes of 1, 2, 3, 7, and 8. And what do you think of class 10 for package detail? Is it worth the cost?
I can't exactly comment on that because I've never implemented that accounting class. So I don't know what exactly the overhead is. Obviously, the overhead is going to vary depending upon the number of packages that a thread might utilize. But it would be wonderful to get that level of detail. I fortunately get enough detail off of the package level stats that I get along with my 7 and 8. So I've never had to go to 10, although it would be nice, but I don't know the cost. Great.
Well, people love your presentation, and Brian sent a note saying he appreciated the plug for his blog entry. Haha. That's hardly a surprise.
Well, it's brilliant and goes into very specific details, so I recommend everyone.
That's great. All right, I'm going to take control back just so I can do the last couple of slides here, which is basically to put up my final polling question, which we always like to ask our fine studio audience, which is, did you learn anything today? We always get a high number.
I learned that I had a bug in one of my slides.
Yeah, that's unfortunate, but I find when I try to actually fix errors in my presentations in course material, I always risk the introduction of more bugs and errors to fix the next time. It's an ongoing process. It's living documents, and I think doing anything release sensitive, as we both do, you're never ever really done, because what you knew last year about this release is fine, but next year there's a new version and everything's changed again.
Yep.
The agony and ecstasy. With that, I will move ahead and once again thank our main sponsor of the show, DBi Software. Thanks for their use of the platform and use of the hall, as we would say. And again, go to their website if you want to learn more about their products. They'd love to have you go do that. And with that, I'll cue the music, and we'll say goodbye. Have a great weekend. Stay safe, everybody.
Take care, everyone.
Whoops. Waiting for the music to start here. Well, that's working well.
Grab the trombone.
Oh, I actually have it in the corner. You can, if I put on my webcam, you'd have seen it. I just had the volume turned down on this media player. There we go. Lots of noise now. And, yeah, the trombone could come out next week. You never know. I'll take care, everyone. See you again next week for the last DB2LU show, LUW show on AI and machine learning on DB2LUW. Take care and thanks, and we'll see you next time on the DB2Night Show.